Oh, maybe it is actually. Guys, can you be quiet, please? We're going to look at this situation because I think this is one that would help to look at together. It might be hard to comprehend some of this, so if you can find this page, this problem 2, simple harmonic motion. This is a situation where you're going to have acceleration that is not constant. Right? When you have projectiles, we said you have constant acceleration. If you launch something up in the air and let it fall back down, the acceleration is constant, negative 9.8 meters per second squared, always in the same direction. When you have a spring going up and down, it's not constant acceleration. So let's think about this carefully here. Let's draw this. We need spring, and we need this. I think we are going to do it. So there's the mass on the bottom of the spring. Okay, so when you have this thing going up and down here, right, like when it's at the top, okay, when it's at the top, right there, which way is it being accelerated? Down, right? Because the spring's not pulling on it anymore up here, but gravity is, so it's being accelerated down. But once it stretches out enough here, which way is it now being accelerated? Up, because the spring is all stretched out and it's going to kind of overcome the acceleration of gravity. So the acceleration is, even just from seeing those 2 points, it's changing as you go here, right? It's changing, it's not constant throughout this whole thing, right? If you just let a ball fall, free fall, it's constantly accelerated down. But here it's going to change as it goes. The velocity changes, right, because it stops for a split second there. It stops for a split second there. The velocity changes as you go, and the position changes. And the fact that the acceleration changes, we're going to look at the rate of change of acceleration, which you've never really probably looked at in physics before, because if your acceleration is constant, negative 9.8 meters per second squared, the rate of change of acceleration is 0, so it doesn't make sense to talk about it. In this situation, it does. The rate of change of acceleration is actually called jerk. The jerk of something, I guess, because the way they describe it in the book, or the analogy they give, is if you're traveling along in your car, which looks like a wagon here, because I don't want to take the time to, that's just, here's you. You're traveling along in a cart. You're traveling along in a cart, and you're standing up in your cart, and you're holding a cup of coffee or something like that. Okay, there's your cup of coffee. Okay, your cart slowly is being accelerated, so it's going faster and faster. Okay? The coffee in your cup doesn't spill until what happens? Well, even if you start to slow down, if you speed up and then you slow down, like the fact that your acceleration is changing is what makes you spill the coffee. If you have a constant acceleration, your speed's changing, but speed changes don't spill the coffee, changes in acceleration, and sudden changes in acceleration. So suddenly now there's a wall or something here, right? And so you're going a certain speed here, and then suddenly your speed is different. That's because the acceleration suddenly changes, right? You're being accelerated forward, and then suddenly you're not anymore. Then all your coffee comes out of here, right? Or the whole cup goes. Actually, you go like that too, but changes in acceleration. Okay, when the jerk is not 0, right, then your acceleration is changing. So before we try and draw some graphs here, now that I got you thinking about that, I don't know why the numbers are on that way. I would call 5, positive 5, the highest point, and the lowest point, negative 5, but they're backwards for some reason on there. When the thing is going up and down here, so we're going to draw a few different curves, and you can superimpose them all if you want. So we have that, and we have this. And we have the first one, let's do in black for the position. It starts at the top, right? I think it starts at the top. I don't know if it says here, but it's released at the top. So the position goes something like this. And the fact that it's 5 cos t, the period is actually 2 pi. That would be pretty hard to do. Really, probably, the period would be something else. But just to keep it simple here for right now, we're pretending that the spring is exactly such that it takes exactly 6.28 seconds to go one complete drop and up. That'd be hard to probably find a spring that does that, but just because we don't want to get into a more complex function that has like cosine of 5t or something like that right now. Okay? Never mind, just don't worry about it. If you weren't worried about it, then don't start worrying about it now. Now you're worried about it. So this is 5 cos t. That's the position. When it is at the top, what's its velocity? We're going to do the velocity in a different color here. What's the velocity? What's the velocity at the beginning when it's at the top? Right? When this thing's at the top, okay, when it's up here, what happened is, how did it get small? Did I make it smaller somehow? I don't know. When it's at the top, what's its velocity? For a split second, it's 0, right? Because it's going up, then it's going down. It has to be 0 in there somewhere. So it's 0 at the top. And then as it's falling down, what's its velocity? It starts falling slowly. It's going fastest through the middle, and then it stops again, right? It's got a negative velocity the whole time, but it comes back up to 0. So this goes down and back up again, right? Once it's at the bottom, it's back to 0. Okay, if I make this negative here, okay. Oh, did I do this backwards here? No, I'm at 5, and then it went down there. And then this is back up here, right? Because then once it's down here, once it's at the bottom, what happens to it? After it stops at the bottom, then it's got a positive velocity. It goes back up to the top, right? And its velocity stops again. So that's that. And I think my scale's no good here, but that's good enough, right? One chunk of the graph. Are we okay with that? Sort of? Some of you don't sound like you're okay with this. You're fine? You're speaking for everyone and saying you're fine? You're fine. Okay. It's going down, so the velocity is negative. That is, I reversed the numbers on there, that's why. Because I didn't like, it's too hard to think about them when they're the other way around. This was the position, right? This is S. The green one is the velocity. What is the function for the velocity here? It's negative 5 sine x, or t. Now we're going to draw the acceleration graph. We should probably write its equation first. What's the equation for the acceleration going to be? What's the derivative of sine? Cos, so this is going to be negative 5 cos t, right? That's the acceleration. Negative 5 cosine means it stops at the bottom. Like the acceleration at the start is very negative, right? Does that make sense? Which way did you say it was being accelerated at the beginning? It's being accelerated down at the beginning in the negative direction. At the top, its acceleration is as negative as it's going to be because it's being accelerated in the negative direction. By the time you get to the bottom, which way is it being accelerated at the bottom? Up, right? So when the position is at the bottom, the acceleration is as positive as it's going to be because it's being pulled up. It's being accelerated up, right? So the acceleration graph looks like this, sort of. My bad drawing, but we'll live with that. That's the acceleration graph because it's being accelerated in the opposite direction to where it is, right? When it's up, it's being accelerated down. When it's down, it's being accelerated up. That's the acceleration graph. And then, of course, we want the last one, which is really hard to think about because it's rate of change of acceleration. If you look at the slope of that red curve, what's happening with it? The rate of change of acceleration, what's the rate of change of acceleration here? Just look at the slopes of the red curve. What is it there? It's 0 there, right? It's 0 here. What is it at this point right here? it's 1, right? The slope in the middle of a trig curve there is 1. It's got its, like, the acceleration is changing the most in the middle. Okay? Hang on. Just think about this. Pretend that this is a ride at the P&E and here's you. Okay? Now you're going to get a little squished when I do this. When is the point in the ride when you go, woo, it's really fun? Or like, which part is really fun? You'd do a better, that was pretty lame being... When is the part where it feels like, whoa, that's, like down here, when it's up here? In the middle. That's the part where it feels like, whoa, you're really dropping quite a bit, right? That's the acceleration is changing the most then. Okay? Take that home and think about it at some point.